Hi, this is Mr. McGovern. This is the fourth video in the electric circuit series where I'm looking at electrical current. So, as in the last video, we talked about the two main quantities we can measure in a circuit, and they are voltage and current. So whereas voltage was a measure of the energy per group of charges, current is the amount of charge flowing past the point in a circuit per second. And a very simple definition that I give is just the speed of the electrons at a point in the circuit. How fast are those electrons moving? Higher current means the electrons are moving faster. Lower current means the electrons are moving slower. So it's a very simple definition. So I can show you a quick video here of a circuit. So we have electrons flowing around the circuit, right? And through this is an ammeter. This measures the rate that they're flowing around. And I can change them to flow faster if I want. You can see those electrons physically moving faster. But the ammeter itself has to be in series in the circuit. The electrons have to flow through it, okay, for things to work. If I try and put an ammeter in parallel, and the issue with this is, and I'll close this junction here, is you see the electrons flow really fast through this and the battery goes on fire. The ammeter itself has very low resistance, okay, so we need to put it in circuit with the bulb, in the series circuit with the bulb, and the reason we do that is because it measures the current without upsetting the rest of the circuit. Okay, low resistance means it doesn't change the measurement when you put it in there. If you put it in an arm by itself and a branch by itself, because it has such low resistance, it's like a short for the circuit. All the electricity wants to flow through it. So ammeters always have to go in series with the component you're measuring it near. So we can look at what the current is at any point in a circuit. So here we have a simple circuit, and you'll notice electrons flow around. If I measure the current anywhere, it's the same. In this case, 0.45, 0.45, 0.45. Doesn't matter if it's before a bulb, in between bulbs, or after bulbs. The current measures the same in a series circuit at all points. That's because those same electrons have to flow through everywhere. So if I'm measuring at one point, they're flowing at the same point as the other. In the parallel circuit, you'll notice that electrons come along and they split up. So some go one way and some go the other way. And because of that, that's why I have current readings less than the total. The total is 1.8, but each individual current is 0.9 and 0.9. So those add to give the total. Now, they're not always necessarily going to be exactly the same, 0.9 and 0.9, as long as they add up to 1.8. There's going to be situations where I have maybe 1 and 0.8, depending on what's in each arm of the circuit. But in parallel, the currents always add to the total. So in series, the current's always the same at all points, and in parallel, the current is split between the two paths, because that's how the electrons go. Some of them go one way and some of them go the other way. So those rules are actually the opposite of the voltage rules, and we'll talk about that in a second. So there's an equation for current, which is kind of your definition. Your definition is the amount of charge flowing past the point in the circuit each second. So I is the symbol for current, and we measure current in amps. Q, remember, is the amount of charge or groups of electrons. That's measured in coulombs. So Q per second, per time. So that's just the amount of or groups of electrons going past every second. So this equation is really a definition. It's the amount of charge flowing past the point every second is current. Current has the symbol I. So in summary, it's the amount of charge flowing past. I really simplified in my head and just say the speed of the electrons. If the electrons are flowing faster, we've got a high current. If the electrons are flowing slower, we've got a low current. The formula is the definition, it's charge per second, and the symbol for current is I. And in series, the total current is the same at all points, and in parallel, the total current is split and it adds up to the total. That is opposite what we see in voltage, and in the next video, I'm going to go through a set of rules called IV diagrams, which kind of remember these ideas of current and remember the ideas of voltage for you. So it makes it very easy to do calculations.